Yeah. Okay. So next one. So this is again very simple. Okay, but very important concept. Okay. So this is the IV characteristics. Okay. So this is the IV characteristics. Okay. So if you see the left side. Okay. Left side. This is negative voltage, right? Sorry.
Yeah.
Left side. Actually, this is negative voltage. Okay. In negative voltage, actually no current. Like if you see here, current. No, this is current actually. Okay. So like here this is what this is current axis. Here you are not finding any current. Current is zero. Okay, for range of voltage it is zero. Okay, so then we'll discuss this later. Okay, but here for this one, okay, for this one, what is happening when voltage increases, current is increasing tremendously. Okay, so that means this is positive current. So
Okay.
here you have what is that? You have a positive value of current. Okay, positive current. Okay, so that's why like we say this diode is non-linear. Okay, did you understand? So can you explain me
Yeah.
what you understood from here?
Okay. It is basically not linear because till one point it will be like zero,
Hmm.
and then sharply it will increase, and otherwise it will be negative linear.
Yeah, actually, this is not ideal, Kal. Okay, this is not ideal. This is actually practical case. Okay, so I'll repeat again. In the left side, okay, voltage is negative, right? Voltage is less than zero. Okay, only a very small amount of current is flowing. Very small. That's equivalent to zero. Okay, so this here what will happen? Diode is off. Actually, here diode is off. So now here what is happening? This case is for voltage greater than zero. Okay, initially current was very small. Okay, current increases very rapidly. Actually, like if you see here, so this point actually this is called cut-in voltage. So you remember this one. This is called cut-in voltage. So this is also called threshold voltage. Okay, so this is also called threshold voltage, the point at where like current is going to increase rapidly. Okay, so generally for silicon diode, no, that threshold voltage is going to be that cut-in voltage is going to be 0.7 volts. Okay, cut-in voltage is 0.7 volts. After 0.7 volts, what is going to happen? Current is going to shoot up exponentially. Okay, so that's why like it's increasing very rapidly. So here what is happening? Diode is on. Diode is on. So you remember after 0.7 current, okay, increases exponentially. Okay, so this one is a bit important. So in that case, diode is going to be on. Okay, so now there is some equation for this one. Okay, this is not, again I'm repeating, this is not ideal case. This is practical case. Okay, so the diode current formula is I is equal to I capital S. Okay, E power V by VT minus 1. So this is very very important. Okay, so now, like in the formula, we have this exponential term, right? This is exponential. This is not linear. That's why like curve is non-linear. Okay, that's why curve is non-linear. Okay, so I also want to tell you some difference between this ideal diode and practical diode. Where to write? Maybe I'll write it here. Okay, so ideal diode. Okay, ideal diode, and you have practical silicon diode. So we are taking both the silicon diodes. Okay, so this ideal diode, it's going to act like a perfect switch. Okay, so perfect switch means like on off. So this is going to act like a perfect switch. Okay, but this one, it will turn on only after, what is that, 0.7, right? It will turn on, okay, at 0.7, after 0.7. Okay, and so this will turn on at 0 volts. Actually this will turn on at 0 volts itself. So this is a practical device. This is not an ideal switch. Okay, so this is the practical device. And so here there is no leakage. In ideal there is no leakage. Okay, but here there is a small leakage current. So here there is small leakage. Okay, so this is what is that, so this is very important. Okay, so now here what happens, they have given this detailed what is that, silicon, sorry, detailed IV characteristics. Okay, so did you understand till now?
Yeah.
Okay. Yeah, so this is fine, I guess. Okay, so here, whatever the graph we had, no, like in the previous one, okay. So this is just IV characteristic. So this is detailed IV. So this is showing which is forward bias, which is reverse bias, what exactly is happening here. Okay, so now here overall idea is nothing but current. Okay, current I versus V. I is in what like y axis, x is in sorry, V is in x axis. Okay, so this is a practical diode, so we are going to compare it with the ideal behavior. Okay, so now again we'll start with this what is that, reverse bias region. Okay, so in reverse bias region, actually I already told voltage is negative, right? Voltage, this is negative voltage, this is minus V. Okay, so there is always a small leakage current. Actually this is small leakage current. Okay, and near zero, actually it will be bit flat, it will be flat. Okay, it's almost what is that, flat. Okay, so here what is happening, diode is off, diode is off till here, but after this region something is happening. Okay, so when you increase this negative voltage to a larger extent, okay, that means when it reaches VBR, minus VBR. Okay, so here what is happening, current is going to increase very sharply, current is going to increase very sharply. Okay, this is called breakdown. Okay, so this is called breakdown. Did you understand what is breakdown?
Yeah.
Okay, so can you explain what's breakdown?
So below this region, right?
Hmm.
It will go in the reverse direction.
Hmm.
If the voltage becomes very negative, it will go to the other side.
Yeah,
If this
generally for voltage, negative voltage, you will have only very small amount of current. Okay, that's leakage current, very small. Even like close to the initially, it will be zero, close to zero. Okay, but when you try to increase this negative voltage, when it reaches this point, that is breakdown voltage region, what is going to happen? Current is going to increase very rapidly. Okay, and this is called breakdown. Okay, did you understand? So this is called breakdown, right?
mm,
So now we'll come to the forward region. Actually, so before turning on means before here. Okay. So in this case, here what is happening? Current is very small, right? Current is very small, that is even close to zero. So current is very small here. Okay, and now what happens when it reaches around 0.7? Okay, so this is what cut in voltage, right? This is what cut in voltage. So after 0.7, what is happening, like it's going to current is going to increase rapidly. Okay, so current increases rapidly, that too exponentially. You can see here this is some exponential. Okay, so here diode is going to be on. Okay, so this curve, if you want to represent it in terms of what is that, an equation, so that's what I have written. So this is I is equal to is e power v divided by vt minus 1. Okay, did you understand? So now this formula is a bit important, so can you explain what are the terms here, what are all, like what?
I am not
Okay, so
sure,
that is fine.
but
No,
it
no, that
will.
is fine. So this is I know I is diode current. Okay, you remember this one. Generally, in many cases, it will be given as small I. It will be even suffix like ID. Okay, so this is diode current. Actually, this is the output current. Okay, so this is output current. Okay, and we have is, right? So we have is is nothing but, I told like there will be some small reverse leakage current, no? So reverse saturation current. Okay, so this is called is nothing but the small amount of reverse saturation current that is existing in the reverse bias region. Okay, so reverse saturation current. And typically, so there is some value also. Okay, it will be in between, you remember, so this will be in between 10 power minus 12 to 10 power minus 9 amps. Okay, so that's why this is very small. Okay, very small. Nano amps, pico amps means like it's very small. Okay, and we have V here. Okay, so that is nothing but the voltage that is applied across the diode. Okay, so we give some voltage across diode, no? Voltage, okay, voltage across diode. Okay, voltage across the diode. So we also have VT. Okay, so you must have known this already. So do you have any idea what is VT? VT is thermal voltage, right? You forgot everything. VT is thermal voltage. Okay, so this is going to be KT divided by Q. Okay, so this is KT by Q. Maybe like I'll open a new. It's writing is a bit difficult here. Okay, so now you see here diode formula is I is equal to capital IS e power. Actually, we'll also have one more term that is N. NB divided by BT minus 1. Okay, so this is what this is diode current. Okay, this is diode current, and this IS. Okay, so this is reverse saturation current. Reverse saturation current. Okay, so we have V here. Okay, so that V is nothing but diode voltage that we have given across the voltage. Okay, so this is diode voltage, and so we have VT. Okay, so VT is nothing but actually VT is thermal voltage. Okay, so VT is thermal voltage. Okay, so there is a value for this VT. Okay, so VT actually it is expressed as KT divided by Q. Okay, KT by Q, actually K is Boltzmann constant. Okay, so T is temperature in Kelvin and Q is the charge. Okay, at room temperature. Okay, room temperature, so this VT is going to be equal to 25 millivolt. Okay, you remember this one, so this is very very important. Okay, at room temperature. Did you understand? Did you understand diode formula? Okay. Actually, and there is one more mistake here. N should be here. N into VT. Okay. Oh, so I forgot to tell about N. No, actually, N is called ideality factor. Okay. N is called ideality factor. Okay, so for generally ideal diode, no, for ideal diode N will be equal to 1. For ideal diode N will be equal to 1, but for real diodes, okay, that means practical diodes, it may vary from 1 to 2. N will vary between 1 to 2. Okay, so did you understand till now? Any doubts till now? Any doubts?
Understood.
Yeah, okay. So actually, now you see in forward bias, okay, in forward bias, I'm writing it as FB. We already know that voltage is greater than 0, right? That voltage is greater than 0. So here, current equation, it will be I into I is equal to IS e power V by, okay, this N into VT. Okay, why? Because this is much greater than 0, no? So like e power infinity is what? E power infinity is what? E power infinity is infinity, right? Did you understand? I'm telling like voltage is very much greater. Okay, voltage is very much greater than 0. Assume that very much greater means what if it's infinity? Okay, so e power, this becomes e power infinity, right? This term becomes totally e power infinity. Actually, we have e power v by nvt minus 1, right? So if this is infinity, if this whole term is infinity, does it make any difference if you subtract minus 1 from it? No, right? If you have infinity, if you're subtracting minus 1, it's not going to make a very big change. Okay, so it's again infinity only. That's why like we are just taking this out from the main equation. So for forward bias, current equation is I is equal to is e power v by eta vt. Did you understand?
Yeah,
Any so if you have any doubts, I can explain again.
it's okay.
Actually, I understood that you didn't understand. Okay, you see here. Uh, okay, what is the formula? Actual formula for ideal current equation? That is I is equal to, right? I is e power v by n vt minus 1. Is this right?
Yeah.
This is equation. So I am telling like in forward bias. So what is forward bias generally?
Uh,
Forward bias means the voltage applied across the diode is greater than 0, right?
right. Yeah.
Okay, so voltage applied across diode is V, right? V is nothing but voltage, diode voltage. Voltage across diode. Okay, so here in forward bias, this V is going to be greater than 0. Okay, so right now I'm telling like greater than 0 means if it's much greater than 0. Okay, assume that this is infinity now. Just assume like it. Okay, it's very much high, no? So I'm assuming the maximum value that it is infinity. Okay, so now what happens if you substitute infinity? Is is equal to e power infinity by n into vt minus 1. Is this right?
Yeah.
Yeah, okay. So now what is e power infinity? So like I'll show you here. So e power infinity or infinite. Okay, so e power infinity is actually infinity here. E power infinity is
Yeah.
infinity. Okay, so that means now this term. Okay, so here in this term you have infinity minus 1. Okay, generally what is infinity? What is the meaning like of infinity? It's very huge
So,
value, right? It's a very large value. Okay, so from a very large value, if you take minus 1, does it make any big difference?
no.
No, right? So here I am going to
No.
generalize the equation that this minus 1 doesn't matter. So I am generalizing and writing I is equivalent to I is e power v divided by vt. Now did you understand? Since this is going to be a
Yeah.
greater value, okay, so this one doesn't matter in forward bias. So in forward bias, current equation, current across the diode becomes I is equal to is e power n into beta t. Understood?
Yeah.
Okay, so now we'll do the same for reverse bias now. Okay, in reverse bias I'm writing it as rb. Actually in reverse bias what is happening, this v, no, voltage across the it's less than 0. Okay, it's less than 0. So now what happens? Okay, so can you tell me now what will happen?
Yeah. Now
Hmm.
it will go from the first negative.
Yeah, actually here this current is going to give only minus is. That means like you can even relate it to technically. No, technically I already told you will have a very small reverse saturation current. Reverse saturation current means it's a negative direction, right? So you can even relate it like that. Okay, so you can remember it like this. In reverse bias, the current across the diode is nothing but the current is equal to minus is. Okay.
Yeah.
So think it like that, small voltage, small current. Like if you increase the current, you will have a slightly, suddenly huge current. Okay, so that's why this is going to act like a switch. Okay, so now that is all about this one. Okay, so can we go to the next? This is again the same thing.
Yeah.
Okay, so now, yeah, here, very good. Okay, so you have I is equal to is e power v by vt. Actually, you will have n. Okay, you will have n. For ideal cases, I is equal to 1. Sorry, n is equal to 1. Okay, so e power v by vt minus 1. Is the saturation current. It is also called scale current. Okay, it is reverse saturation current or scale current or just saturation current. Okay, Vt is the thermal voltage, Vt is kT by Q. Okay, so if you substitute, so this will be 25 millivolts. Okay, so here this is 0.08 into T, right? 0.0862. Okay, so if you substitute, this is T 300 Kelvin, no, you will get Vt as 25 millivolts. Vt equivalent to 25 millivolts. Did you understand? Do you have any doubts here?
I think. But
What?